The students that you're about to see are in the Science Fair Saturdays program, which is a joint project of Sibley Center and Riverbend Community Math Center. The kids basically get a chance to learn a lot of different basic skills like programming and electronics, building things, a little bit about entrepreneurship, science. They are invited to create their own projects. The kids always come up with fantastic ideas, and we love to see what they do.
So what I built is a 4-bit adder. This adder is fully self-contained. It doesn't require any computer to make it function. So this adder worked in binary, which if you don't know what binary is, it's simply, the base 10 is, you have these slots. This is a zeros, this is a ones place, tens place, hundreds, and thousands place. Binary doesn't work this way. Binary is, this is the ones place, this is the twos place, the fours place, the eighths place, this is the 16th place. So this means that if you have this number in binary, this means that this is 1, it doesn't have a 1. This is a 2, it has a 2. This is an 8, it has an 8. So this would be 10 in base 10. This adder works in binary. So the switches on the side control the input to the adder. Switches 1, 2, 3, and 4 control the first number in binary. So if I wanted to input 10, I would do, this is on, turn this thing off, this is on, this is off. This would be 10 in base 10. And switches 5, 6, 7, and 8 control the second number in the binary adder. So when I turn this on, suddenly, if I turn these all off, you see that nothing's lit. That means that a 0 plus 0, 0 plus 0 is 0. If I turn all of them on, this is 15, which is 1 plus 2 plus 4 plus 8, 15. And that would be 1 plus 2 plus 4 plus 8, 15 is 30. So this is off, that's, you don't add a 1. 2 plus 4 plus 8 plus 16, that's 30. But how does this work? 0 plus 0, so 1, 1. So 0 plus 0, that's easy, that's 0. 0 plus 1, that's also easy, that's 1. So 1 plus 0, that's 1. So 1 plus 1, that's actually 1, 0. 1, 0 in binary is 2 in base 10. So how do we represent this in this circuit? So we divide this table into 2. We divide this into the regular table, which is 0 plus 0, 1, 1, that'd be 0, 1, 1, that'd be 0, because this 0 here, we're going to use that 0 and put it here. The second table is we use 0, 1, 0, 1. Alright, that would be 0, 0, 0, 1, because this 1 here goes to here. Let's call this the carry, and let's call this the regular. So in this table, so let's say this table, let's add a base 10 number. Let's say 52 plus 61. How do we do this? So we use the addition table, which you have memorized, which is 2 plus 1, what's that? That's 3. So and this, that would be, so there's no carry here. But 5 plus, that's 11. 5 plus 6, that's 11. Put the 1 here and we carry it, the 1 here. This is like the carry over here. The 1, that's 113. For, if we were to add 2 binary numbers, we do 1, 0, 1, 0, and let's say 1, 0, 1. Actually 1, 1, 1. Do that. 1 plus 0, that's 1. 0 plus 1, that's 1. You see 0 plus 1, 1. 1 plus 1, what's that? 1 plus 1. 1 plus 1, that's 1, 0. 1, 0. That's the carry. So 0 plus 1 plus 1. What's that? That would be 0 plus 1 would be 1. 1 plus 1 would be 1, 0. So 0, 1. 1 plus 1, that's 0, 1. That's how addition works in binary. So now you get a basic idea of how this thing works. So on to how does the adder work? So to represent this process in binary, we have to use gates. Gates are basically an electronics term for something, for a machine that takes in two inputs and outputs another. These inputs have to be 1 or 0, and 1 or 0 or 1. And this is a 0 or 1 output, just like binary. So for this table, we have to use a special gate called a XOR gate. This XOR gate takes two inputs and outputs 1. So the XOR gate, if it's 0 and 0, it outputs 0. If it's 1 and 0, it outputs 1. If it's 0 and 1, it outputs 1. If it's 1 and 1, it outputs 0. So that's for this regular table. But for the carry table, we have to use an AND gate. The AND gate takes two inputs and outputs 1, just like the XOR gate. But for the AND gate, it outputs 1 if and only if both of the inputs are also 1. Anything else, it outputs 0. 0, 1, outputs 0. So how do we use this? X is the X and Y. Let's say these are the two switches, 4 and 8. They're the ones place in the two numbers that I'm going to add. So Y, let's say Y is 1, X is 0. So 0 goes to here, and this is an AND gate. So and Y is 1. This is the carry table. Let's say 0 and 1, 0 and 1, 0, 1, 0. This outputs a 0. 1 and 0, that outputs a 1, because 1, 1, 0, 1. So 1, 0, so this goes first, just like the carry in base 10. So that's 0, 1. That would be the sum between 1 and 0 and 1, which is 0 plus 1 is 1. So that's 1. Now how does this work? This is what we call a half adder. This will work for one digit binary numbers. But if you notice, this has no input to calculate the carry from a previous half adder. So if you look at the base 10 again, you add these together. Let's do a different sum. Let's do 55 plus 77. 5 plus 7, that's 12. So this 1 goes up here. So 5 plus 7, that would be 12. But you add that 1, so that's 13. 132. So we need a way to add that 1 in to the sum. We have to, let's do this again with 1 and 1. So 1 and 1. 1 and 1, that would be 1, 0. If it would be 1 and 1, that would be 1, 0. How do we add that 1 into the next adder? That way we have to use a full adder. You can think of a full adder as two of these put together, since we have to add this plus this plus this. So what we do is we do 1, 2, 3. 3 inputs, that would be X, Y, and the carry from the previous half adder, which is this. So we add that and we split this. So we first add these together and a half adder. You already know. Put this here. It's backward. Okay, so that's that, and that's that. That's the say this is 1 and 0, for example. That would be 1 and 0. So then we take this, and we have the carry, and we add this, which is the regular sum, and these together, like this, and this. that and this. Okay, so let's say the carry is 1 from the previous one because it's 1, 0. This would be 1 plus 1. We have that. We already know this. It is 1, 0. So then what we have is we have the carry from this is 0. We have the sum, which is this plus this plus this, which is 1, 0. That would be 2 in base 10. This 1 plus 1 is 2. So what we do is we take this and this. So we add this together. So we take an OR gate, which is we take these two. If any one of these two inputs is 1, we make that into a 1. So none of these are 1. So it's a 0. 1, 0. That's 2. This entire thing is what we call a full adder. Half adder, full adder. So this, for binary, this is the addition table. We have 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1, 0. So we split this into two tables. For this we have to use a GOR gate. For this we have to use an AND gate. So we put these together, take these two inputs, 0 plus 1 would be 0. That's for the addition table, that's 0 plus 1 would be 1. So this doesn't have a carry for the previous number, so we take this full adder. This has an input for the carry. We add these three numbers together and get an output. So for this, we take all this 4-digit binary number and this 4-digit binary number, and we put each one of these digits, through a full adder. So this adds all the digits together in the binary number and it outputs to these LEDs. Because I like electronics, and so I'm not that good at programming Arduino and stuff. So that's connected to a computer. And so this is completely self-contained. It doesn't need a computer at all. This works on its own. So I feel this was cool because A, it worked on its own, and B, it just does a simple job, like so excellently, and it's easy to explain. And so B, it's also a really good exercise on electronics because this taught me a lot about gates and other electronics. So like also about binary, which I didn't know much about until I did this project. So it has taught me a lot, and I think I will use these skills I learned from this project in the future.